Okay, so we started with the idea of a free particle, and we ended up with the concept of a field and a Lagrangian for that field, which can be written as phi dot squared over 2, where phi represents the field, minus 1/2. Let's do a three-dimensional. We've been doing a one-dimensional, so let's just write this for a three-dimensional system. So it's a grad phi squared minus this constant times the field value squared. And maybe we can write this in another way where we're not breaking this up into space and time terms. So that would look like, let's leave these derivatives in terms of the summation convention. So that's a partial derivative of the field. We sum over b. That'll take account of these two terms. Right, there's a minus sign between the two here because of the metric. And then we have minus m squared over 2 phi squared. Of course, when we look for the equations of motion, we end up with, let's write this as an operator on phi. So the two derivatives in time, we get a minus del squared, and we have a plus m squared phi, and that ends up being equal to 0. And we could also write this using this notation. In that case, it would look like we could capture these two terms as two partial derivatives plus m squared on phi is equal to 0. Let's look for a general solution of this. Of course, these are plane wave-like solutions, and right, the quantum physics comes in where let's just write this as proportional to some delta function, right? The uncertainty relation for the system, and this ended up bringing in the A and A cross operators, and so we have the solution. Now we have 4 space-time dimensions, and we'll specify what this k is. So we have a normalization factor associated with the 4 space-time dimensions, and here's the A operator, and we have an e to the minus I. Maybe we could write this in terms of k. Let's just write it in terms of notation that we're familiar with, 3 plus 1 notation, where we break up the, this is a 4-vector squared, if you will. We'll write that in a second. Plus a cross e to the I, same thing, k dot r minus omega t. Here, so we're saying that Ka is a 4-vector, and it has energy and momentum in it. So this is really, if energy is h bar times omega, h bar is 1. H bar and c are 1, so it's just the frequency, and that's the wave number. Looks like that. Ka, right, it's the k squared, the summation convention, that gives us m squared, right? That's just a relativistic energy equation, right? E squared equals p squared plus m squared with factors of c equal to 1. and so h bar as well. All right, E equals h bar omega, so this becomes omega squared. H bar is 1. This is P is h bar times k, so it's just k squared for h bar equal to 1 plus m squared. And so this thing is just omega squared minus k squared, and of course that's equal to m squared. So another thing we can write this as ka minus m squared, of course, trivially comes from that, is equal to 0. And we want our general solution to obey this dispersion relation. So let's write phi is equal to dk4. So these are all of these quantities in here. There are 4 of them, right? There's frequency and wave number there, represented by that. Our notation isn't really consistent because then here we didn't write this as, we could write this as KA. Sorry, not KA. KAXA, where X is a 4 vector that involves time and position, right? So you get an omega, right? XA is a time position vector, so you get the omega t minus kr, or the other way around, kr minus omega t, depending on your metric. Okay, so we have dk to the 4th, 2 pi to the 4th. We want to insist on this. We want to bring in a delta function that captures this, and we won't go into all the details here. There's a factor of 2 pi here, delta ka minus m squared to establish this. So this is 0 if this is not obeyed, and infinite if it is, and therefore it'll pick out that value of ka. And then we have the same stuff that we have here, a e to the minus I blah blah. Maybe we'll write this as KAXA. Hopefully I didn't make a mistake there. Well, we can just define that. Well, not really, but, well, I think that's right. Plus a cross e to the I KAXA. I will close this off. And, okay, so that looks all right. But now we also want to, if you remember at the beginning of this, we recognized, let's go back to what we wrote here. We have it here that these energies, and therefore these frequencies, can be either positive or negative when we solve for them. So we only want positive energies because we don't know what to do with these negative energies. And so we will insist on omega greater than 0, right? So in other words, the energy is positive, and we'll have to do some reinterpretation for these negative energy solutions. So the solutions for the field that obeys special relativity and quantum physics becomes 1 over 2 pi, right? We're fixing the value of the energy, dk to the 4th. We have this constraint from the dispersion relation, and now we insist that the energy be positive. So we'll write down what this step function is. I think we can call it that. e to the minus I KAXA plus a cross e to the I k, I don't know, maybe we can change the index. It's just an index that we sum over. It looks like that, and this phi of k naught is, it's the thing that picks this out and says it's okay, it's just 1 if k naught is positive or 0, or it's 0 if it's negative. And we won't go through this derivation, but dk for delta, this term ka minus m squared, theta k naught, ends up being, so I broke this up into these, the 3 spatial and 1 time. We get 2k naught delta k naught minus omega k, and therefore this is dk3 over 2k naught. Sorry, what did I do there? dk3 over 2 omega k. Right, this delta function, it's omega k. And so the solution looks like dk3 2 pi cubed 1 over 2 omega k, a e to the minus I k c x c plus a cross e to the I k c x c. And now we have to do some interpretation. So we're combining the ideas of relativity and quantum physics. We had the commutation relations. That seems fairly straightforward. But we did something here that doesn't seem to be completely straightforward. And so now we interpret these 2 terms. Right, so this term looks like, we have annihilation and creation operators, ladder operators. And so we have an incoming mode, right? We have an incoming mode here, and that annihilates. And then we have an outgoing mode, and that that creates, but this annihilates particles, and this creates anti-particles, so that we can reinterpret the negative energy that we've forced into a positive energy.